In this tutorial, we will be discussing acidic strength and calculating pH. Acids and bases can be classified as strong or weak depending on their ability to dissociate in water. If you don't remember, the word dissociate means that it's going to break down into its ions. For instance, HCl here will break down into H plus and Cl minus. However, you'll notice that the H plus gloms onto the H2O to make H3O plus. The word strong indicates a complete dissociation. You'll notice the single direction arrow to the product side. The weak indicates a partial dissociation. In other words, not all of the HF is going to break up into H and F. And as a result, you have a double-sided arrow to indicate that. The H plus ions, or protons, produced in an acid are very reactive. If we think about what hydrogen is, the typical isotope of hydrogen has a mass number of 1 and an atomic number of 1, meaning that there are no neutrons there. All it is 1 proton and 1 electron. Some of the isotopes do have neutrons, such as hydrogen 2 or hydrogen 3. However, the most typical one does not. Once that electron leaves, all you have left is a proton. As a result, it tries to glom onto other things, primarily water. So you'll notice that the H3O attaches itself to water to produce H3O. You will hear the terms H plus, proton, and hydronium or H3O plus all used interchangeably, meaning the exact same thing, because it's all getting to the point where we're looking at H plus. Now remember, back in previous lessons we've talked about equilibrium constants. That's where the concentration of the products is divided by the concentration of the reactants, and that comes out to be K. Well, Ka is the equilibrium constant for the dissociation of an acid in water. So Ha is the generic symbol for an acid. A for acid, and H for the hydrogen that's being given off. Once it dissociates, we have H to the minus 1 because it's lost that hydrogen, and then that hydrogen has attached itself to the water to form H3O. The strength of an acid is indicated by the magnitude, the numerical value of the equilibrium constant. The larger the Ka means the stronger the acid. If you have a weak acid, it has a Ka of a very small number, less than 1. So in other words, 0.000, so on and so forth. This results in a very small amount of H plus or H3O plus being created on the right-hand side. Let's look at the equilibrium constant, the K for this. It's the products of the reactants. We have A minus, A to the negative 1, H3O plus. Those are the products over the reactants, which is HA, and water. Well, water is in liquid form, so therefore it's not included in the equilibrium constant, which is why we have this value here. As the acid is stronger, the numbers on top here are going to be bigger because it's going towards the products. It's breaking down more and more. That's going to make the overall K larger. If the reactants are smaller, or if the Ka is smaller, if the acid is weaker, then these numbers on top are going to get smaller, hence making the K smaller. So let's look at the words strong and weak as you're reading. Strong means there's a complete dissociation in water, approximately 100%, whereas weak has a partial dissociation in water. Because of the dissociation makes strong electrolytes. A lot of charges are floating around, whereas the weak has a weak electrolyte. As an example here, we have nitric acid. The hydrogen is given off from the nitrate, where the water then absorbs it. Notice the single direction arrow. Same with the base. Calcium hydroxide has 2 hydroxides and 1 calcium when it's dissolved in water. Acetic acid on the right-hand side gives off that hydrogen at the end. But because of that double-sided arrow, we know that it's a very weak dissociation. Kb is the equilibrium constant of the dissociation of a base in water. So here's our base, the H2O. One of the hydrogens from the water comes over to be BH plus and OH minus. The strength of the base is indicated by the magnitude or numerical value of the equilibrium constant once again. The larger the Kb means the stronger the base. The weaker the Kb, the weaker the base, the smaller the Kb. Remember, less than 1 is referring to 0.0000 something. And this results in a very small value for OH minus. Just like the Ka, we have the equilibrium constant here of BH plus OH minus over B. Acid and base strength can also be determined by Ka, the acid ionization constant, and Kb, the base ionization constant, respectively. Ka, if it's less than 1, indicates a weak acid, meaning that the reactants are favored. If it's greater than 1, it means it's a strong acid, which means the products are favored, which means it'll be going to the right. Kb, if it's less than 1, is a weak base. If it's greater than 1, it's a strong base. Let's take a minute to talk about water specifically. Water is amphoteric. Water's acidic and basic behavior is a result of its environment. It can act as either an acid or a base, meaning amphoteric. That's what that word means. So it has a transferable H ion in the molecule. It also has a pair of electrons from the oxygen to absorb a hydrogen. So if we look at this first example, the hydrogen from the HCl is getting absorbed into H3O+, meaning that the water is now acting as a base as it absorbs the hydrogen. Here, it gives off a hydrogen, meaning that it's acting as an acid. Water is an extremely weak electrolyte. About 1 out of every 10 million water molecules form ions through a process called autoionization, meaning that's going to break up into its ions automatically without any other addition to the solution. If we look at the equilibrium constant for this, it's the products over the reactants. So H3O plus OH minus over the reactants, but the reactant is a liquid, so we don't include this in the equilibrium constant. So this is then equal to 1 times 10 to the negative 14. This equation becomes very important when we start doing pH calculations. The equilibrium constant for water's autoionization is given as Kw. This is called the ion product of water. H3O plus times OH minus is equal to 1 times 10 to the negative 14. Notice it says at 25 degrees. Remember that as the temperature changes, the equilibrium constant can also change. If one of the concentrations is known or has been measured, then the other concentration can be determined using this equation. So as H3O plus increases, OH minus must then decrease, so the product stays constant because they're inversely proportional. pKs are ways to express the strength of an acid or base as well. pKs are the log values of the ionization constant. If you look on your calculator, you will see the word log on one of your buttons. You need to be using this button as you're determining these. The stronger the acid, the smaller the pKa. The stronger the acid, the larger the Ka, and then the smaller the pKa. This is because this is the negative log of Ka. Once again, the stronger the base, the larger the Kb, which results in the smaller the pKb. Using the rule of multiple equilibria, we can say K is equal to K1 times K2 times K3 and so on and so forth. Well, because of that, we can say Ka times Kb is equal to Kw, or pKw is equal to pKa times pKb. So on a neutral equation, H3O plus and OH minus are going to be equal to each other at 1 times 10 to the negative 7. That means if you multiply these numbers together, it comes out to be 1 times 10 to the negative 14. Well, the log value of this is 14. So that means pH plus pOH is 14. Remember, P is referring to that log. The pH scale is a compact way to specify the acidity of a solution. pH is the negative of the log of the concentration of H3O plus and OH minus. So notice that as the number gets smaller, remember this is times 10 to the whatever, so 0.01, 0.001, 0.0001. As those numbers get smaller, the pH gets bigger. The pH is the negative log of the hydronium concentration. In a neutral solution, the hydronium and the hydroxide are going to be the same, which is equal to the 1 times 10 to the negative 7. If we take the pH of this, we find that the log of 1 times 10 to the negative 7 is 7 for water at room temperature. This is neutral. To put that into your calculator, my calculator may be slightly different than yours, but for what I have to do for my calculator, I put 1 EE negative 7, then I push the log button, and then I take the opposite sign of that. And that's where that negative comes in. The normal range for pH is from 0 to 14. pH can be negative, which would be very, very acidic, and it can be larger than 14, very, very alkaline. pH is less than 7 is acidic, more than 7 is basic, and 7 is neutral. So from this side here, it's acidic. This side here is basic. The lower the pH, the more acidic the solution. The higher the pH, the more basic the solution. Remember that 1 pH unit corresponds to a factor of 10 in acidity. So in the concentration of hydrogen. So pOH is another way of looking at this. Remember that pH was the concentration of the hydronium ion, while pOH is the concentration is based on the concentration of the hydroxide ion. It's the negative log of OH minus. Notice the correspondence of OH here and OH here. Make sure you match those up when you're solving for answers. pOH is equal to the negative log of 10 to the negative 7 for neutral water. So that means the pOH will equal 7 at neutral water. You need to know the OH minus to find the pOH, just like you need to know the H plus concentration to find the pH. pOH of less than 7 is basic, greater than 7 is acidic, and pOH of 7 is neutral. So if you look here, pH is the top row, pOH is the bottom row. 0 for the pH is the same as 14. They're basically reverse of each other. Strong acids or strong bases are assumed to totally disassociate in water. Therefore, the molarity of a strong acid of the H plus ion concentration will be used when solving for pH. Make sure that you calculate this correctly. Because if you have a diprotic strong acid, then you're going to have twice as many hydrogens there than you would otherwise. Same thing with bases. Trihydroxy base means that you're going to have 3 times the molarity once it's dissolved in water. So let's do a few examples of these before we finish. Calculate the OH minus concentration for each solution, we're only doing one here, and determine whether the solution is acidic, basic, or neutral. Personally, I like to look at the pH. I don't like, if I do pH and pOH and interchange them, I end up confusing myself, so I like to stick with one. So before I calculate the OH minus, I'm going to go ahead and calculate the pH. So pH is negative log of H3O plus. So that means pH is equal to negative log of 7.5 times 10 to the negative 5. To put this in my calculator, I would put 7.5 EE negative 5. I might have to push the equal sign before I continue, depending on your calculator. And then push the log button. That comes out to be negative 4.2. The pH is the opposite of this. So 2 negatives cancel each other out to be positive 4.2. Now to find the OH minus concentration, as we said before, the H3O plus times the OH minus is equal to 1 times 10 to the negative 14. I could plug the H3O plus concentration in there and solve for the OH. So 1 times 10 to the negative 14 divided by 7.5 times 10 to the negative 5. The OH minus concentration then comes out to be 1.33 times 10 to the negative 10. Let's do a few more. Calculate the pH of each solution at 25 degrees Celsius and indicate whether the solution is acidic or basic. So all I want to do is calculate the pH this time. I don't care about the OH minus concentration. So pH is negative log of 1.8 times 10 to the negative 4. Put that into my calculator, 1.8 times 10 EE negative 4, log button. Take the opposite sign, comes out to be 3.74, meaning it's acidic, because it's less than 7. This one, they gave me my OH minus concentration. Well, to solve for pH, I need the hydronium concentration instead. So before I do anything else, I need to solve for that. Getting a step ahead of myself. Okay, H3O times OH minus is equal to 1 times 10 to the negative 14. So H3O is equal to 1 times 10 to the negative 14 over 1.3 times 10 to the negative 2. That comes out to be 7.69 times 10 to the negative 13. I can then put this into the calculator, 7.69 EE negative 13, push the log button and take the opposite sign, and the pH comes out to be 12.11, which, because it's above 7, means that it's basic. Finally, our last example. Calculate the H3O plus concentration of a solution with a pH of 4.8. We're doing the reverse now. So 4.8 is equal to negative log of X, what we're looking for. So first thing I want to do is get rid of that negative sign. So negative 4.80 is equal to log of x. You should have a button on your calculator that says inverse or second function, something like that. And your button on your calculator should say log and then slash 10 to the x or something along those lines. Or second function 10 to the x. That 10 to the x reverses this process. So the whole thing with the pH is basically knowing how to use your calculator. So 10 to the x cancels the log out, and we're only left over with x at the end. In negative 4.8, 10 to the x comes out to be 1.56 times 10 to the negative 5. And that gives you an overview of strong versus weak acids and bases and how to calculate for pH.